Everybody, in this video we're going to start the last chapter in the textbook, which is the convective mass transfer correlation. And as the name implies, you can easily tell that we are going to talk about some correlations that we use to calculate the mass transfer coefficient. And before we go into the details, I would like to make this video as an introductory video, because this is there are some important points that I want to emphasize in this video and make sure that they're clear for the audiences. So before we start, this is a quick revision on the or summary of the relations that we discussed before. We have this flux equation, which is or says that the flux is the mass transfer coefficient multiplied by the driving force, and we have these dimensionless parameters. We talked about these dimensionless parameters and the physical meaning of each one of them, and we mentioned earlier that there was a necessity of having these dimensionless parameters because of the many or the parameters that affect the mass transfer coefficient are many, and that's why we cannot study the effect of each one of them separately. So we had to group them into dimensionless parameters to make it possible for us to do this this analysis or do the experiments to get the mass transfer coefficient. So we have discussed them in deep details in chapter 26, and that's why I'm not going to go into these details anymore. You're free to check it if you're interested. So finally we were able to get this relation, which is the relation between Sherwood number, Reynolds number, and Schmidt number, which takes this form in case of forced convection, and Sherwood number with Grashof and Schmidt number in case of natural convection. And we said the values of A, B, and C depend mainly on the fluid properties, on the flow regime, and on the geometry of the system where mass transfer takes place. So if you recall in the previous chapter 27, we always had the problems with the mass transfer coefficient given. So we had it as kx, kl, kg, or ky, whatever the shape of the mass transfer coefficient or the units, but it's already given, and that's why we didn't bother to calculate the mass transfer coefficient. The only trick that we had was to get another form of the mass transfer coefficient of the same phase, to get kl from kx or kg from ky, something like this. But in this chapter we will be more concerned with calculating the mass transfer coefficient itself. So this chapter will cover the correlations of convective mass transfer coefficient that was obtained experimentally. So if you recall, in chapter 26 we discussed some methods to calculate the mass transfer coefficient for flat plate, and the methods or one of the methods or two of them had some theoretical background, like the exact boundary layer analysis. In this case we had a theory, we had an equation that we started with, and we were able to get the mass transfer coefficient at the end from this theory. But what we get here is based on published data or published papers or whatever that was based on experimental work. So the scientists did experiments and get data, and from data they were able to fit the data with the equations to get the form of the equation that fits with the system and with the geometry, and it's taking into account all the parameters that we discussed before. So this is we will see that the mass transfer coefficient equations that we will get are valid for fluid moving around different geometries, and again, as we said, or again, this will be valid for different mass transfer processes, whether it's evaporation, condensation, whether it's sublimation, it's dissolution in a liquid, whatever the mass transfer process is, it's gonna be valid. And again, the mass transfer coefficient takes into account the geometry, flow regime, and fluid properties, and this is something that we will see clearly when we go through the equations. You'll see the equation for the same system would have a form in case of liquid and another form in case of solid. In case of gas. We will see forms of the equations for laminar flow and for turbulent flow for the same system. So this is going to be a nice thing to see for different cases. And for all the equation, most of them will be put in the form of dimensionless parameters, as we mentioned earlier. So now we will go to the point that I want to discuss here in some details, which is the correlations themselves. So the textbook have I think 6 sections where in this chapter, where each section is concerned with a group or a type of equations that is covered in this part. And here we have 4 of them. 4 of these sections we will cover the mass transfer in plates, spheres, and cylinders, in flow-through pipes, in case of weighted wall column, in packed and fluidized bed. And there are 2 more sections I'm not gonna cover in this series. And also there are many other cases that are not covered in the textbook, and this is the point that I want to make. So to start, I just want you to know that this chapter is one of the most boring chapters in the textbook, at least for me. This chapter has nothing to be discussed or to be illustrated. It is just giving correlations. So it's mainly just listing the correlations for each one of these systems. So you will see here in case of plates, it will tell you if you have a laminar flow, then you will use this equation. If it's fluid is liquid, then use this correlation. If it's vapor or if it's a sphere, you will use this correlation. So it's just listing the correlation. So there is nothing that you can discuss. I'll try in some cases to give some background about the system. So like in case of weighted wall column, I'll give a discussion what is the weighted wall column, why we use it. In the packed and fluidized bed, I'll give you some like quick information about the packed column and why we use it and what is the fluidized bed. So I'm gonna try my best to make it informative as much as I can. So in case you don't understand what is this, you will have a good idea before you go through the equations. But at the end of the day, this is gonna be just listing equations. That's why what we will do here in these 4 sections is going to be exactly like what we'll do in the following 2 sections, and that's why I thought it's just enough for us to go through these sections. The other point here is that there are some things that will be useful to learn here. It's not related to mass transfer as mass transfer, but it's related to using the equations and substitution of the equations. So for instance, in case of dealing with any one of these systems, you have to be aware of the conditions of your problem so that you can pick the proper equation that you can use for your system. If you are using another equation, then you're solving another system assuming that it's yours. So this is one thing. The other is how to pick the physical properties, because it's very, very important. In case this one thing that we'll see in case of having a fluid that or a liquid that is evaporating. So if the liquid is evaporating, then you have 2 phases, the liquid and the gas phase. So you have to understand which phase you are concerned with and which properties you are going to use. If it's is it the liquid properties or is it the gas properties? This is one thing that you have to keep in mind. The other thing is that the textbook didn't give you all the correlations that are available in literature. There are many correlations that you will see, and or you will find if you do a quick search on the internet, you will see that there are like tens of equations and correlations that scientists produce based on their experimental results or experimental research. So you cannot rely on the textbook as the source that has everything. So the textbook is giving you some equations to get you familiar with these kind of equations and dealing with the equations and using the equations properly, but still it's your homework. If you need to calculate a mass transfer coefficient for a specific system, it's your homework to do this research yourself. You have to search for the equations, see what is the system or what are the equations that are suitable for your system. So this is one other thing. So what we will do starting next video is we will go through the first section, which is mass transfer to plates, spheres, and cylinders. So I'll see you then, inshallah. Goodbye.